Primero hacemos la ronda, grabamos desde el principio, así no nos olvidamos. Comienza a grabar. Okay, welcome everybody. Some familiar faces. So it's good, means people likes the environment. So this is the agenda for today. Okay, there's a 2 days course. We'll start with a round table, okay, both people in person and online. Then we will follow with an introduction to COMPS and with an introduction on the PyComs syntax. Then we'll have a coffee break. Claudia, there will be some coffee or not? Okay, there will be some coffee. And then we will continue with some hands-on with the Jupyter notebooks with Javi. Then we'll have the lunch break, which is on your own, okay? And then we will continue with a session on machine learning. That will be 2 parts. Fernando will explain a little bit of theory around this lib, and then we will do a hands-on, okay? You can take all the slides. Principally, if they are not there, that will be during today and tomorrow. The slides and material will be in this folder, which you can take the QR or copy the link, okay? I leave you 1 second to take the picture or the link. Then today we finish at 4:30, and tomorrow we start at the same time. Tomorrow we will restart with a session on using provenance, the feature that is able to record provenance of the workflows in PyComs, okay, with Raul. Then Frances Lordan will present the new deployment of the runtime COMPS agent. Again, we have a break, and then we will have multiple hands-on in Mare Nostrum. We will start with the settings of the hands-on, and then Javi will lead the hands-on on Mare Nostrum on the regular use of PyComs. Then we have the lunch break, and then another hands-on on the COMPS agent deployment. Okay, you will see a little bit the difference, and then on the provenance, and then the conclusions and final notes. Okay. Okay, so we will start with the round table. Maybe we will start from the back. Let us know who you are and where do you come from.
Colombia, working in this department in work phenomenon and now using by conflict strategy.
I'm Alberta, I just joined process group, so
Hi, my name is Christian. I'm from also the workforce and distributed computing team. I work primarily on this lead and other projects with integrating GPU support into this lib library. And today I will be giving the section 5 of hands-on with this. So see you later.
hello, my name is Fernando. I'm also part of the process group. I'm working with this group and also my dissertation, and I'm going to read the section number 4.
I'm Paula. I just recently joined the virtual group and I'm going to be part of the
What's your name? Sorry.
Alexandra Mara.
Okay. Hello.
So, and I'm working with the science.
Right, so thank you. Welcome. Tu mateix, Lluís.
Hello, my name is Cesar. I am coming from computational dynamics and the PhD is regarding the pre-diagnosis of diabetes types 2. And now we know that COMPS works well with CPUs, but as you know, Lightfox is working now at BSc, my nostrum, and we would like to use the GPUs. And I will be focalizing in using GPUs from CPUs with the Python.
Hey, I'm Nicola. I'm from the Swiss Technological Institute, and we're using PyComps in the project DTGO.
Hi, my name is Johannes. I'm actually managing exactly this project in DTGO. And yeah, I'm just here to learn a bit more about the new features of PyComps.
Yeah, hello, my name is Thomas. I also recently joined BSc as a postdoc, and my background is in numerical linear algebra.
Hello, my name is Hector, and I joined like 1 month ago the KC department, the wave phenomena group.
My name is Ruth. I'm also in the wave phenomena group in BSc. And I'm here to learn about this most.
Molt bé. Good to know.
Hello, I'm Cedric. I also work with Ruth and Hector.
Ahora.
Within the Laplace group, wave phenomena, and I'm actually reading the books.
You need to study more.
Yeah, my name is E from Lincoln Stroke. And but I'm still trying to learn new methodologies.
But what's your background, just to understand?
I'm biologist.
A biologist,
Yeah.
okay.
Yeah.
Bueno,
Still I study bioinformatics, but I don't have.
And they use R for this.
molt bé. Usen R.
I am Daniel Lexia from the same group here, Rosa. I'm here to support the attendees in the development of the application. I also work in DTGO. And I thought it's also with library and other projects.
Hello, I'm Charlie. I'm also from Rosa's group, and I'm a postdoc in one of the projects.
Finally, I am Javier Conejero, Javi. I am senior researcher as well in the Rosa's group, and I'm leading the development of the Python interface for COMPS, as well as other bindings that Rosa has just mentioned, like for R and quantum things.
I'm Rosa Badia, also from the BSc. I'm leading the workforce and distributed computing group, and mainly leading also these COMPS developments. Now we'll try with people. Okay, some of them have started to write. I see Michael Credenti. I am an HPC application developer at Chineca, Bologna. Then Georgina Diaz. Hi everyone, I'm Gina. I worked at the BSc case department with the wave phenomena group as a senior software engineer. Giving support to different projects, we use PyComps in uses for EQ project, and I want to learn more about how it works. Then we have Joan Hereu. Hi Joan from Barcelona, currently working on innovation at BSc. My background is on energy engineering, sustainability, and climate. Then we have Adria Quintanas Corominas. I'm Adria from Girona. I am postdoctoral researcher at BSc in the case department. I'm currently using PyComps in some projects from the synthetic data generation. Pietro Morichetti. Hi, I'm Pietro from BSc Computer Science Department. I'm involved in the Near Data project, and I'm here to learn about PyComps and understand its potential. Then we have Amir Bozoui. I'm Amir from BGS in the DevOps team. I do scripting and managing the KH clusters, Kubernetes. just got involved in DTGO and interested in PyComs, needed to know more in this subject. Carlos Arnedo. I am Carlos Arnedo. I'm a junior research engineer in the physical and numerical modeling group at Case Department from BSc. Erika De Paolo. Hi, I'm Erika De Paolo. I'm a geophysicist at the Etna Volcano Observatory. I'm currently working on PyComs workflow for an AI-based monitoring system. Said Abdel Monsef. I am Said. I'm a postdoc at the University of Girona. And I work in Celestis project and work on simulations and finite element modeling. I'm currently using PyComs in Node 3. Vale. Rebecca Bruni, I'm Rebecca. I am working at INGB in Pisa. I work in the project DTGO for volcanic unrest. Hafiza Kanwal. Hi, I'm Hafiza Kanwal Chanjua, PhD in telecommunications engineering. With title in building cognitive orchestration for MEC and IoTs. I'm a postdoc researcher in BSc in PPC group, working about designing the orchestrator for 5G application and services and distributed computing architecture. I'm interested to learn COMPS to extend my knowledge in distributed computing. And then we have Frances Lordan, which is from our group. I am Frances Lordan. I'm a researcher in BSc working in the COMPS runtime. And tomorrow I will be presenting some of the sessions and giving support to the attendants. Dimitar Penkov. I am Dimitar from Bulgaria. I am currently an HPC student at UPC, part of the EU Master for HPC program. I have research experience with EEG and ECOG data, training a neuromorphic spiking neural network. Okay. Anybody else online? Dr. Dimitar? 19 people online. I don't know if we have. If everybody has introduced los problemas a la traducción. Puedo hacer desde aquí, ¿no? ¿Sí? Okay. So thank you everybody and welcome. If at any time you cannot hear us correctly, I don't know how was the sound from the people in the room. We have an external mic, but let's see how it works. And we will start with the lessons, okay? We're a little bit ahead of scheduling, but this is okay, because usually we tend to get delays. Okay, I'll start with the motivation. Try to connect my laser point. Pequeños. Como cambiarme la si funciona. Bueno, no sé. No, con este cuerpo. Sí, porque si no, lo pondré yo los juegos atrás. Okay. So we'll start with motivation for PyComs, okay? So we see that every time we have new computing paradigms emerging, no, from the already known clusters and supercomputers, now moving to the digital continuum, where we have sensors and instruments in the edge, okay? Edge devices, fog devices, computation in the network, no, in a very distributed network, and also HPC, exascale computing, quantum computing coming, the cloud, no. And another characteristic of this digital continuum is that we have resources, no, devices that can appear and disappear. I mean that they can join the infrastructure and leave, no. So it's a very dynamic environment. And so it's a challenge how to dynamically add and remove these devices from the infrastructure. No? We have also new architectures coming. Some years ago, we had the GPUs, and also FPGAs, tensor units. We have the quantum computing, no? And each of them different way of programming them. Also, not only the devices are different, sometimes different type of computations. So traditional HPC is programmed with MPI, C, Fortran, but big data and AI are more programmed with PyComs, with specific environments, different type of data structures. Okay, so there is a lot of heterogeneity on how a developer faces how to implement their applications. No, and this is difficult for the programmers. No, and especially if programmers are not computing scientists. No, it's from another field, and they want to develop applications. No, and there is a high course to program the applications, but also to leverage the actual performance that the system can achieve. No, it's not only, so you have three phases, no, when developing an application. That is correct, the syntax is correct, and you can compile, no, and it executes. The second is that it runs, but the third one would be that actually it gets some performance, because sometimes I have students that say, but it's correct, it compiles. Yeah, the fact that it's correct, it doesn't mean that compiles doesn't mean that it's correct. And third, the fact that it's correct doesn't mean that it's performant, because sometimes you can have very slow parallel applications, even they are parallel, no? Because they are not written in an efficient way. No? So, and also it's this, no? It's difficult to understand what is happening. No? If you have an application and you turn the return and you submit, no, or you execute, no, it's not finishing. What is going on? No, what is happening? Why is going so slow? No? It's difficult to see what's happening. No? Maybe you think, it was fast. No, it took 5 minutes, but maybe it's 5 minutes for a very small data set. When you run it with a larger data set, maybe it's much more slower. No, so it's relative. The fact that it's faster or not is relative. No, that we have to look if it's efficient. No? So a little bit, this was our motivation, no, to start developing these programming environment tools, to provide tools that allow developers to focus on your problem. No? I want to run a simulation of an earthquake. I want to have a workflow that starts after an event of a volcanic event, no? For example, or I want to do the training of a machine learning experiment model, no? After getting some simulations from Alien, no? Things like this, and that this can be easy, no? Provide this intermediate layer, this programming layer, and let the difficult parts to optimize, to distribute the data, to distribute the computations, to orchestrate the whole computations that are done through the runtime. Okay. And then also the architecture specifics, no? If it's a GPU, or if it's a CPU, or if it's a different storage system, that the runtime can take care of all of this. No? In addition, we have some tools that helps on understanding. We have tools for monitoring. This you will see the monitor with the Jupyter notebooks, and also performance analysis trace files. No, at BSc we have a whole group that works on tools for help on the performance analysis of applications, and basically is based on the generation of trace files. No, a trace file is a postmortem information of what have happened in the application, and you have very detailed information of all the events when have happened in each processor, etc. And then you can go and analyze this with detail. And we have then that the runtime is able to generate these trace files, no, that can be analyzed with this other tool that is called Parallel. And the other thing is that we have been working on integrating these different type of workloads, no, and it's not the same at pure HPC simulation and modeling than machine learning or data analytics, no, and the idea is how to make it easier to integrate all these. No? And a little bit, this is the summary of the view on programming models that we have at the BSc. No? Also in the top you have the applications, and the idea is to provide this high level abstract interface to the application developers. And then here have a runtime that is intelligent, no? Is capable of making decisions on doing the multiple functions. And finally, an API that can run in different type of infrastructures. Okay. So then you can focus on developing your application on the actual problem without having to think about the underlying infrastructure. This programming interface should be general purpose, okay, that you can use it for any type of application. We are not focusing in a single type of applications. And then it's based on, we will see a little bit what it means a task, but it's task-based. The parallelism is at the task level. And it has also this feature that we show to the develop application as if there was a single shared memory space. And then we have the runtime that is intelligent, we'll say, no? It's able to find the parallelism, in this case at the task level, distribute the data, it's interoperable between different type of infrastructures, etc. And this same idea at the BSc has been applied to different programming models, no? So today we will be talking about COMPS, which works better in, say, more distributed environments and with large coarse grain tasks, no? Tasks that take some amount of time, no? Say from 10 milliseconds to 1 day. But we have also OMS, no? And a little bit this is the difference, no? The basic idea would be the same. Both of them are task-based, no? The parallelism is based on tasks, and also has this automatic generation of the, well, we'll see that the task graph and look for the dependencies. But we have different granularities, no? The tasks here are much smaller in OMS. The data dependencies also in the case of the OMS is more dealing only with memory space, but in COMPS we deal both with objects and files. And also for the programming languages, OMS is more on the traditional HPC languages, C and Fortran. In COMPS we deal with Java, C, Python, and we have a prototype for R that maybe next year we can start talking about, okay? So then what is COMPS? Okay, I've been giving some ideas, but let's focus a little bit more on what is COMPS. The idea is to be able to program sequential code, okay, with a general purpose programming language like Python is the one that we will be focusing today, for example. And then we identify the tasks, no? What is a task in PyCOMPS is a method, or in COMPS in general, is a method, no, a function in your code that you annotate with this decorator, in this case, the task. No? And what is the characteristic of this task? Well, it has to have some granularity. By granularity, we mean that it takes a little bit of time to compute. It cannot be just an instruction, because if not, the overheads of creating the task will not be enough, no? And the other thing is that typically, not always, but typically you will call multiple times to this function. No? Here, for example, we have a matrix multiplication, which have 3 nested loops, and we are calling to the function multiply a lot of times, no? As many as blocks has the, as many as the blocks that has the matrix, plus even another time, because we do row by column for each of the elements of the blocks of the matrix, no? And in this case, ABC are not elements like integers, individual integers or floats. It's already a block of data, no? So we are doing the matrix multiplication by blocks, no? So the multiplication here, the multiply, already takes some time because it's already doing the multiplication of 2 blocks and writing the result in a third block. No? And what happens is that if I have this multiplication and I have 2 parameters A, B, and a third parameter C, what I'm indicating in this annotation is that C is an in-out. It means that this parameter C is read and written by the function, okay? A and B, if I don't say anything, it means that both of them are only read, okay? And we see this inside, no? we do A by B and multiply them and add to the value of C. No? We are accumulating on top of C. And this in out, then if we have another in multiplication instance that also has the same parameter C, we will have a data dependence between them because we will need the result of the previous instance of this function, okay, to do this computation. No? And this is what we call a data dependence. So the difference with other task-based programming models where they do not detect the data dependencies is this: in a back of task paradigm that they call it, they will run all the tasks completely in parallel. But here we take into account the data dependencies between tasks, okay? So at execution time, every time we call one of these tasks, the runtime will look if there is one of the parameters that needs to be, that is generated in another task. In case this is happening, it will add an edge in the task graph. No? So here in the task graph, what we have is one node for each of the functions that are tasks, and edges represent the data dependencies between them. Okay? We will go through this with more examples later, but just that you have a first idea. Another concept that is important is that you don't need to care a lot for where the data is. Okay, you need to indicate in your functions the data that you want to access and the directionality. But then, if this is already instantiated in the program, the runtime will take care of moving the data between the nodes of the computation. So you don't need to move the data to the node where it's going to be executed. And once we have the task graph, what happens is that here we see which tasks can run in parallel and which runs need to run one after the other. So here in the example, we have these first tasks that are one after the other because they have data dependencies. They cannot run in parallel. They will have to run one after the other. But once we are reaching the area of the green tasks, this potentially can run all of them in parallel between them. No? And every time one of these green tasks finishes, the subsequent red task can start. Okay, so this dynamically defines the parallelism and the sequentiality that needs to be respected. No? So if the task graph is defining like a partial order of execution of the tasks, it doesn't mean that if you have these, I think there are 16 tasks, green tasks, that all of them will run in parallel, because also it will depend on the number of resources you have. If you're running in a node that has 8 processors and each of them can run one task, you will run 8 at a time, okay? It's quite a small example in this case, no? Typically we have larger graphs, but it's just to understand, okay? And then also it's important to understand that sometimes we will run a task that has been generated later in the code before others that have been generated earlier. No? For example, imagine that the scheduling decides to go through these chains of tasks, no? One after the others. When I finish the green, I start the red, then the brown, etc., the yellow. And maybe one of these green tasks on the other side are left to later, no? Because maybe here the policy can say, okay, if I run this chain of tasks, I'm exploiting the locality because I will be reading the result of a previous task, and I don't have to move data, no? So it may happen that the actual order of execution of the task is not exactly the one that is that the order that we have specified when writing the code. No? If the dependencies allow for this, and there is a policy, the scaling policy that decides this, the order can be different. Okay. And in general, that the programming model is agnostic of the actual infrastructure. You can do a smaller test in your laptop, okay, even with the Jupyter notebooks. Then when it's ready, you can move it to the support computer. Maybe you have to change some things, and of course it will make sense if the data set is larger. No, typically you will not be able to run with a large data set in your laptop, but maybe with a test data set, you can run it in your laptop and then move the same application to the supercomputer or to the cloud. No? Another important aspect of COMPS is that the task can already be parallel. No? We can have sequential tasks that are simple Python or C or Java code, or we can have tasks that already have threading inside. Just because, for example, if you use NumPy, you are multiplying, like the example, no, 2 blocks of NumPy. The libraries, the numerical libraries that execute these multiplications, a lot of them are already implemented with OpenMP, for example, that have parallelism already there. No? So if we give some threads to this task, it can run in parallel already the task. No? But we also support invocation of tasks that are parallel programs. No? Like in the Calestis case, we are calling simulators, the LP simulator, which is parallel. And also the same happens with the uses for AQ. No? When we call Salbus, Salbus is a parallel programming model, but still this is a task in our another workflow. No? So it allows to combine different types of tasks, sequential, parallel inside the node, or parallel between nodes. Okay? Other things that are supported, for example, is streaming. No? Data that is on the form of a stream, like a video from a camera, no? That is multiple images, no? One after the other. This can be sent to a task, and the task is able to understand this. We have some failure management. We'll show an example later in the syntax examples. And also we have this machine learning library, this lib, that we will talk about it. Okay? And we have Mare Nostrum installed in multiple supercomputers in Europe, now also at least in one in the States. No? I think also in Fugaku was installed. So here only mentioned Europe, but in fact it has been installed in other in other worldwide infrastructures. Okay. Okay. Then one important aspect of the programming model is that it comes with a runtime. Okay, so it's composed of 2 big parts. No, we have the syntax that we will be explaining and so on, but then you need to understand also a little bit how the runtime work, because sometimes you will need to write the code taking into account this. No. So basically what we do is that PyCOMPS application is executed as master worker, following the master worker paradigm. No? So you will have in the computation infrastructure one node that acts as the master and starts executing the application, and will start also the runtime in that node. Okay? And then the others will act as workers and basically will receive tasks for execution. Okay? Actually, in Mare Nostrum, for example, since it's a very big node, no, each of the nodes are very big, have 112 processors. Usually, we don't use a single node just for the runtime. Usually, we put also there a worker. Okay, so we have in that time we have in that case we have in the same node the master and a worker, no, and the other nodes will act as workers. In Mare Nostrum, you will see that this is submitted as a whole application inside the supercomputer, and we have a specific script that submits this for execution in a node. Okay. Then the execution starts with your code, which is in principle sequential, and every time we call one of the methods that have been annotated as task, we will add a node in the task graph, no, in each of them. And the runtime will look also for the data dependencies and add the corresponding edges. And when we don't wait for the whole graph to be generated. Once we have a piece of the task graph, we will start executing the task, no? Deciding in which node we have to execute this task. If there is data that needs to be moved from the main node where the main program is to the other nodes, and other decisions. No? And every time a task finishes, the runtime receive a notification about this, and we will make new decisions. No? Basically, this is how it works in a very simple idea. No? Some of the features we have, for example, sometimes they ask me, what are the differences between PyCOMPs and other similar programming models? One is first that is very tailored, or a lot of, well, we also work in the continuum, but we have many functionalities that are tailored to HPC systems, okay? And others is that it allows different type of tasks. For example, we can define the constraints, which is a way also of defining the different type of parallelism that I was telling, no? Because when we say here that this task has this constraint of compute units equal 8, is because we need the task at least to have 8 cores. In this case, it's an MPI task, which actually will have 16 nodes by 8. But if it was not an MPI task, it will mean that requires 8 cores. No? But we can also use the constraints to define that the task requires an amount of memory. This happens many times with life science applications, which take quite a lot of memory, or that you require a specific performance or architecture. No? Like here, I don't have an example, but for the GPU task, you will see that we need to add here also that it requires a GPU. Then we have these MPI annotations that help on these cases where we are calling an external function that is an MPI simulation. And we have these annotations also for the failure management. No? In this case, if there is a task that fails, by default, we don't stop the whole workflow. Before we were doing this, but some users told us, okay, but maybe we don't care if one task failed because we are sending an ensemble of simulations, and if one fails, I just want to know that this has failed, but you can continue the execution of the others. No? So a little bit is what this interface allows you to say. No? In this case, also it will cancel the successors of that node of that task. Okay, so we will like cancel a chain of tasks. With regard to the interface with machine learning, well, in principle, just because it's written in Python and a lot of the machine learning packages are written in Python, already integration is easier. No? But also we have developed this additional annotation and software to help on the integration with other type of packages, and specifically with machine learning. And in particular, we also have this Leap machine learning library, which is a machine learning library, not a deep learning library, not a traditional machine learning library that has methods like clustering, classification, etc., which is parallelized with Python. Okay, so and we will present a little bit of this in the afternoon. And overall, also we have a whole environment. Okay, you will see today. Well, I think also will show a trace, but you will see for sure the Jupyter Notebooks interface. Okay, and you will be able to play with it in the notebooks hands-on, and the monitor, which shows, for example, the task graph that is generated and the data dependencies and more information about the execution of your application. And then you can also generate trace files, which then you need to visualize them with Paraver. In this case, the tool monitor the Jupyter Notebooks works with a browser. For Paraver, in Mare Nostrum, we have the Paraver already installed, but you can also install it in your laptop if you want. Okay, okay, just to summarize. So COMPSs provide this programming environment for workflows or parallel applications, which enable this integration between HPC, the traditional HPC, but also with big data machine learning. We also tried that the environment supports what we call dynamic workflows. And what I mean by dynamic workflows, for example, I explained it, the fault tolerance before, no? So this fault tolerance gives some dynamism, no, to the workflow, because the workflow that it will be finally executed maybe is not exactly the one that we have written in the code, because maybe we designed it for 100 simulations, but actually it runs with less. But also you can use it, this fault tolerant mechanism, to design like branch and bound mechanism. No, I can define that I have a tree that is opening a lot of options, but when a task fails, decide that that branch is killed. No? So it can be used for this type of things. Also, it supports a dynamic resource management, depending on the workload, you will see how this is done, for example, in the COMPS agents environment, where you can dynamically add nodes and remove them from the infrastructure, okay? And it has also support for data streaming. We are not showing this today, but just that you are aware, no? And also on Thursday and Friday, there are 2 additional courses on DataClay and Ecuba, which are libraries for persistent storage. One is key value and the other is object oriented. If anybody is interested in learning them, just like to let you know that PyComs is well integrated with them. So you can then use PyComs to access this data in DataClay. And this is some projects that we are involved in. Okay, just to have a knowledge. Okay, and here in this other QR is also the documentation of COMPS that in principle today you will not need because it will be very guided, but if you want to browse it or use it later. And we will be also be giving a chipset for the advanced functionalities. I don't know if I give it now or maybe I can give it now before I start the syntax. So people have. So don't read it now because it's the advanced features, but ¿tienes una tú? Repartir, Xavi? Is there any question? There are more here if you need, if I didn't give enough. Vale, yo. Now I need to see. Albert.
What happened if one of the tasks reaches those?
Yeah.
Or,
In fact, it gets stuck, no?
yes.
This is a point of failure. Espera. The question was, what happens if the constraint reaches the limit, no? If it cannot be fulfilled with the current infrastructure.
The task gets stuck until some other resources are released, and then it will be executed. A common mistake can be to select more resources from the constraint that the actual machine has. And in that case, since it can never be fulfilled, it will be stuck forever.
Okay, now I need to switch to my environment for the lesson. So
But it doesn't fail.
yeah.
Okay, Frances is pointing out that it doesn't fail, and in a couple of minutes, it does a stop, a control stop.
Okay. So there is a timeout there.
Yes. It's a strange case because we usually know the infrastructure where we are executing, but if you made that mistake, then you will see that you will receive an error message saying that the task would not be scheduled.
So you can. You the same as me, okay. So I need to share which one I said. Okay.